everybody, it's Math Monday when we analyze a concrete algorithm. David, can I use that word, algorithm?
It's more of an equation.
Equation! Cancel the algorithm. And what I love about these concrete equations is that we're trying to mimic what's going on in the physical world by using numbers. And to do that, we've got to take some assumptions, and that's going to be part of our discussion today. So today, we're looking at an equation that's used in a process to determine if we've got adequate joint spacing in our concrete pavements. And David, what's a number that we normally... David, why don't you just come on in and join me? So we're looking at this equation today that's available through the Federal Aviation Association.
It sounds right.
And it's looking at two separate equations to identify, is our concrete going to be okay with respect to transverse cracking?
Right.
And basically, the more space we put between joints, the higher the tendency for transverse cracking.
Right.
So we've got this variable L, which stands for, I'm not looking at my notes, the radius of relative stiffness. David, can you explain the radius of relative stiffness?
Well, it pretty much boils down to these two terms. This is E, the modulus of elasticity of concrete,
Right.
or essentially its stiffness.
Okay.
This is the modulus of subgrade reaction of soil, or essentially the stiffness of the soil. So it kind of boils down to the ratio of the concrete to the ratio of the soil. And then there's a few corrections or rules of thumb. This is the thickness, so as the thickness gets thicker, it makes a little difference. This Poisson's ratio isn't going to make a whole lot of difference because it's almost constant with concrete. And so that's basically it. We're going to take the ratio of the two moduli and adjust them a little bit for the thickness. That's basically what it boils down to.
Now, after that, once we get that value, bear in mind, we're actually going to run through some numbers with y'all real quick. Doing so, once we get that L value, we're going to plug in joint spacing in inches, so we should already have some known value. We're just checking it, divided by this relative stiffness, radius of relative stiffness, and that has to be less than 5.
Right. Well, you could use it as a design parameter. I mean, once we know this, we can calculate the maximum joint spacing.
Right, and to calculate that, what we've got here is our values where our modulus of elasticity for our concrete was 4 million. Was it our H? We said was excuse me, 9 inches.
9 inches.
Our Poisson's ratio was 0.15.
Right.
And our K was 200 cubic inches. What that gave us was an L equal to 33 inches. We take that value and we plug it into this bad boy. So our joint spacing we assumed was 20 feet.
Yeah.
20 feet in inches is 240 inches. Excuse me, sir. So 240 inches divided by 33 inches is going to be approximately 8.
So 20 feet.
Not good.
Not good.
Not good.
Too big.
So you have to reduce the size to get that joint spacing over L less than 5 to come in with that safety region. Again, what David pointed out, this L is a comparison of the stiffness of our concrete to the stiffness of our soil with some correction.
Right. And as a design parameter, we can do that quickly. We can take 5 times 33, 165 inches.
Right.
So we know now that if we had 165 here, that would be 5. So joint spacing would be,
And change.
12-ish, 15-ish.
Yeah.
Yeah, 15 would be 160. So 15 feet would work, 20 would not.
And more often than not, people are using 10 to 15 feet for their joint spacing.
15 very common. 15 very common.
Right. And that makes sense.
Makes perfect sense.
All right, well, thanks for joining us today. We had a great time. What we're going to show you here is all the variables that we use, and hopefully we spelled all the words correctly. One of the things that bothers me about this, David, is these two values. I don't like those values because it is forcing us to assume that they're never going to change. I mean, there are even values in the FAA that tells you this is 4 million, this is 0.15, and what's the problem with that, David?
Well, not all concrete's the same. I mean, so we looked at typical values that we suggested as an example. We plugged those in. 4 million typical value, but it's not what all concrete is. That's why this is a variable. 0.15, I might call that 0.2 myself, from work we did at the Bureau Lab. So it's good that they're variables. We plugged them in some typical values just to give you an idea, but if it was me, I'd use real values for real projects.
And the reason why we want to use real values for real projects, yeah, it's going to cost money to find those values out. I mean, 28, 56, and 90-day modulus elasticity test is not inexpensive, but if you're doing this type of project where you have to be concerned about it, it shouldn't be that big a deal. Some of the newer materials that we're using, carbon nanotubes, steel fibers, I mean, there's some newer things of older technologies that help us enhance concrete and change these values up significantly, which could save time. I mean, what if you can spread out your spacing to whatever value, let's say 20, 25, 30 feet. I mean, that saves time and money.
No doubt. You and I always talk about, more data is better science. More data can be cheaper construction.
So faster construction too, which means more money in your pocket. So
that's right.
Anyway.
Yeah, let's build real structures with real data.
Building concrete, saving the world. That's what it's all about.
That's what it's all about.
So if you have any questions, you have any concrete concerns, don't forget to like, subscribe, and check out the awesome variables where everything is spelled correctly.
I'm David.
I'm John. Go concrete.
Beat asphalt.
Okay.